Okay, everybody, I thought we would look at a couple of more examples. I might have went over things a little bit too quickly in 1.1, and some of you have expressed some concerns about some of the questions at the end of the homework. So I'll just go over a couple more examples here and at least get them set up. Let's look at number 55 out of your book. We have an open rectangular box with a volume of 2 cubic meters. So a good thing to do is to draw a picture and try and get an idea of what's going on here. Here's a box, and remember, it's open on the top here. So this top part is open, and we know that the total volume, V, is equal to 2 cubic meters. So volume is equal to 2. Now we want to express the surface area as a function of the length of a side of the base. Well, we know that the base is square. So that means if we represent one side as x, we can represent the other side as x. Now the thing that we don't know is the height. Let's call the height y. That's what we don't know. But we do know that the volume of the box is going to be given by length times width times height. So it's x times y, or x squared y, and that has to equal 2. Well, that means that the height y in terms of x is equal to 2 divided by x squared. Now, what's the surface area going to be if we call S of x the surface area? Well, then we can say that S of x is going to be what? Well, we're going to need the surface area of the bottom of the box. That's just x by x, so that's x squared. Plus, we're going to have the four sides. This side right here has an area of x by y. Same with this side, same with the back side, and same with the side on the left. So we're going to have 4 of these sides that are x times y. But we want everything in terms of x. We want everything as a function of the length of a side of the base, which is x. So we're going to have then x squared plus 4 times x times y, which is the same as 2 over x squared. And what happens then? Well, these x's, x over x squared divides to just 1 over x, and we're left with a surface area of x squared plus 8 over x. So there's the formula for the surface area. Now, for the domain, you're going to want to think about, well, what's the smallest that x can be in practical terms? In practical terms, I mean, x, it can't be nothing. You have to have some sort of dimension to it. And of course, also in algebraic terms, you have to think about not being able to divide by 0. Okay, let's take a look at number 56. You have one like this in your homework as well. Here we have what's called the Norman window. It's basically a rectangle surmounted by a semicircle, and we're given that x represents the width of the window. So this is going to be x down here. And since this is a semicircle, we know then that the radius here of this semicircle is going to be x over 2. Alright, so we're also told that the perimeter, P, is equal to 30, and the unit on that is feet. So how do you find perimeter of an object? Well, you add up the distance around. What's the perimeter going to be in terms of x? Well, it's going to be this distance down here, so that's x, plus, well, this distance right here, actually 2 of these. We don't know what those are. Let's give those a name. We'll call them y. So we have 2 y's. Plus, well, let's see, we're going to have a circumference, I guess, of half of this circle. So remember, the circumference of a circle is 2 times pi times r. So we want half of that. So that's 2 times pi times r over 2, which is just pi times r. And so the half of the circumference is equal to pi times the radius, which is given by x over 2. So that is what the circumference of that half circle is going to be. So that's pi times x over 2. Now again, what is this equal to? Well, it's equal to 30. And so from this we can solve for y, which we're going to need in order to be able to determine the area. Because the area is going to be the area of the rectangle times the area of the semicircle. So we're going to solve this for y. And when we do that, what do we get? Well, let's just go ahead and let's see. How about I just rewrite it for right now? X plus 2y plus pi x over 2 equals 30. Let's clear that 2 out of everything. Multiply everything by 2. So that gives me 2x plus 4y plus just pi times x equals 2 times the right side of the equation as well as 60. So solving this for y, looks like we have 4y equals 60 minus 2x minus pi times x, and dividing everything by 4 then gives us y. So y is 60 minus 2x minus pi times x, all divided by 4. If you like, you can divide each thing by 4. 60 divided by 4 is 15. 2x over 4 is x over 2, and pi x over 4. And now from that, we are ready to find the area. The area of this thing is going to be, well, it's going to be x times y. That's the area of the rectangle, plus the area of the semicircle. What's the area of a circle? Well, the area of a circle is equal to pi r squared, so we want half of that because we just have half of that semicircle, or half of that circle, just a semicircle. So it's going to be plus pi times the radius. Well, the radius is x over 2 squared, all that divided by 2. So the area then is equal to x times y, but in place of y we can put 15 minus x over 2 minus pi x over 4 plus pi times, if we square this quantity here, we have x squared over 4, and then all that divided by 2. So our area then is equal to, if we distribute this x through here, we have 15x minus x squared over 2 minus pi x squared over 4 plus pi x squared over 8. When we just take this pi over 2 times x squared over 4, we get pi x squared over 8. And so if we combine those like terms of a negative pi x squared over 4 and a positive pi x squared over 8, that will give us an area that is equal to, let's see, 15x minus x squared over 2. Let's see, this is a negative fourth plus a positive 8. That'll leave us with a negative eighth of pi x squared over 2. So this is probably a good way to leave the area function in terms of the width of the window x for this Norman window. So in other words, if we know what the width of that window x is, of this window, we can find the entire area of the window by just plugging that x into this formula down here. Let's take a look at number 57. Here we have a flat piece of cardboard, and what we do is we cut out 4 corners out of this piece of cardboard, and each of the 4 corners we cut out an x by x little square. Little x by x square. The original piece of cardboard was a 20 by 12 piece of cardboard, 20 inches by 12 inches. What we do then is we're going to fold up basically along these dotted lines here, and you can see if we were to do that, we would get a little box. So let's go ahead and make our little box. And they show you a picture of that, a diagram, in the book. Well, we want to express the volume of the box as a function of x. Well, now the volume is equal to the length times the width times the height. So let's call this the length here, let's call this the width here, and call this the height here. Well, what is the length equal to? Well, if this is the length here, this corresponds, this dotted line right here corresponds to this length side of the box. Well, that was a total distance of 20 minus those 2 x's. So the length L is equal to 20 minus 2x. How about the width? Well, if the width, let's say the width here corresponds to this dotted line, what is this width equal to? Well, it's equal to the full 12 minus these 2 x's here, minus these 2 x's. So the width is 12 minus 2x. And what's the height equal to? Well, the height, you can see, is just where we fold up these sides. The height is just going to be x itself. So the volume is going to be that length of 20 minus 2x times the width of 12 minus 2x times x. And I'll leave it to you to go ahead and simplify that if you want to multiply that out. I don't think you necessarily have to, but it might be a good exercise to multiply those 3 quantities together. And also I'm going to leave it to you to think about the volume in terms of the context of the problem. In terms of the function v of x, our volume is dependent upon x. Well, x can be anything we want it to be. There's no problem here in this formula, this particular formula for x. We don't have any algebraic problems. You can put any real number in for x, you'll get a real number out. The problem lies in the physical limitations of x given the situation of this box. What's the biggest x could be? How far in could we come? And what's the smallest x could be? The biggest x could be and the smallest x could be. If you had a 20 by 12 box, I mean, obviously, if you want to make a box, you're going to have x be something. So x is going to have to be positive. That's one limitation on your domain. But how big can you go? How far can you go before you've destroyed the cardboard box and you can't make anything out of it? So that's what you need to think about for your domain. And finally, a couple words about even and odd functions. Remember that even functions are functions where f of negative x is equal to f of x. In other words, if you replace x with negative x in the formula and simplify it, you get the exact same thing as the original formula. What that means graphically is that the function is going to look exactly the same on both sides of the y-axis. So the y-axis is your line of symmetry, which means, for example, that if we have the point, say, 1, 2, 3, comma, 1, well, let's say it's 2. So say the point 3, comma 2 is a point on our graph. Well, because of the symmetry, if I go to negative 1, 2, 3, negative 3, and go up 2, I'll also have a point on my graph. Okay? Because f of negative 3 has to equal f of positive 3. And if we know that f of positive 3 is 2, then we also know that f of negative 3 must be 2. Now, if you look at an odd function, well, we also have some symmetry. It's not symmetry about the y-axis. What it is symmetry about the origin. Remember that f of negative x equals negative f of x is how we can tell algebraically whether or not we have an odd function. We can tell it graphically by looking at the function and seeing that everything that happens in the first quadrant up here is mirrored in the third quadrant. Everything that happens in the second quadrant upper left is mirrored in the fourth quadrant lower right. In other words, an example would look like this. This would be an example of an odd function. You can see that if you just look at this first quadrant up here, it's mirrored down in this lower quadrant, lower left. If you look at the upper left quadrant here, it's just a little bump. It's mirrored in the lower right quadrant, just a little bump, but going down. And so for the point, say the point right here, this is the point maybe 4, comma 3. So we go 1, 2, 3, 4, and then up 1, 2, 3. We're just kind of showing for example's sake. Well, if that's the case, then f of negative 4 is going to equal negative f of positive 4, which will be negative f, will be negative 3. In other words, graphically, negative 1, 2, 3, 4 will map down to negative 3. So if 4, 3 is a point on our graph, then negative 4, negative 3 is a point on our graph if the function is odd. Okay, I hope this helps you get through 6.1.1 homework. Please feel free to contact me if you have any questions.